Hello, Dr. Su. Good morning. This is Bindushree Adalam. Today, I'm going to present my project on vehicle routing problem. So, first, let's see the overview of the presentation. First, we'll be seeing the introduction of the project, that is about vehicle routing problem. Then we'll be seeing the solving methods available for solving VRP, and then the design of the project, then the experiment, geographical data, result, and finally the summary, that is conclusion and future work. So first, let's see what's VRP. Say your fleet has 100 trucks and you have to drop a delivery plan for 100 trucks and 1000 locations every day. Your plan must minimize the cost and at the same time maximize efficiency. So how do you do that? This is exactly the question of VRP. This is one of the most difficult math problems to solve when you have to consider multiple constraints like the number of vehicles, vehicle capacity, time window of stores, type of goods, human resources, traffic, and road conditions. When you solve VRP, you can improve vehicle utilization, which means you can transport more goods in one go. Consequently, your fleet traveling time will be reduced, so you'll save lots of logistic costs. Coming to the real world use cases for VRP, VRP is a common use case for businesses that deal with some kind of transportation, such as food delivery, package delivery, personal transportation, technician scheduling, where employees need to travel in order to perform some kind of service task, etc. Formally, it is an optimization problem that seeks to service number of customers with a fleet of vehicles. In real life, each use case comes with a unique set of additional constraints. Next, let's see the type of VRPs. We have capacitated ERP, where the vehicle capacities are limited. Then we have multiple depot VRP, where the vehicle fleet is distributed over a number of depots. And then we have split delivery VRP, where the same customer is allowed to be served by different vehicles. And then we have VRP with time windows, where the customer is only able to accept the delivery during a certain time window. And then we have VRP with uh, pickup and delivery, backhauls, etc. In this project, we'll be mainly focusing on capacitated VRP. Next, coming to the solution methods available for solving VRP. Basically, we have two main approaches for solving VRP. The first one is exact approach. The goal of exact approach is to design algorithms that can find the optimal solution most efficiently. They are rarely used for practical applications. Due to the difficulty of VRP, it takes them unreasonably long to find solution for even moderate sized problems. So they are slow. Example of exact approach algorithms or branch and bound algorithms. Then coming, the next one is heuristic approach. Heuristic approaches are designed to provide solutions quickly by trading optimality for speed. So while they only produce an approximation of the optimal solution, you can get something you can use to solve that problem at hand, and you can get it in a reasonably short amount of time. Then we have meta heuristics. Meta heuristics is nothing but the subset of heuristic approach. These are the methods for controlling the basic heuristic algorithm with a goal of exploring the search space most efficiently. One of the characteristics is that they are not problem specific. This is the key reason why meta heuristic approach is taken. Then we have the local search algorithm, which is one of the example of meta heuristic algorithm. So here we'll be seeing what the local search algorithm does. Local search algorithm starts from an initial solution and evolves the single solution into a mostly better and better solution. It uses a single search path of solutions, but not a search tree. Since the local search needs to start from an initialized solution, it's usually required to configure construction heuristics phase before it. So here basically there are 4 steps. Local search tries a number of moves on the current solution and picks the best accepted move as the step. And then we have move selector, which decides the step. That is, what it does is it selects the possible moves of the current solution. Then the acceptor, it filters the unacceptable moves. And then we have forager, which gathers accepted moves and picks the next step from them. The solver remembers the best solution it has encountered through the entire search path. Each time the current solution is better than the last best solution, the current solution is cloned and referenced to as a new best solution. Coming to the VRP mechanism, this is the basic VRP mechanism we'll be seeing in this project. It has a depot. Depot is nothing but the starting point of the problem. Each node here represents the demand locations. It must have a demand greater than 0. And we have the routes here. Routes are nothing but the paths that the vehicle should follow to get to the demand locations. Then we have arcs, which represent a route from one node to another. Then now let's see the neighborhood operations which we'll be using in this project. The first one is before and after procedure swap. Swap procedure takes 2 different nodes and swaps these nodes. This operation is easiest and it is mainly and it is used in many problems which are solved using the local search. So you can see here that the nodes 4 and 5 are swapped here. So, and as a result of which we are avoiding this cross path. So basically the advantage here is it allows us to get rid of the between route X crossings as we can see in this figure here. And it is both the in and between route operation. The next one is reverse edge procedure. It takes 2 different nodes which have a common route and reverses the subroute including both the nodes. So here you can see the subroute is 6 by 4. Now it is reversed so that it forms 4, 5, 6 as the route. As a result of which we are avoiding this crossing, X crossing here, as you can see in the figure. So the main advantage here is that usually we see X crossings, which can be fixed by applying this operation without violating capacity constraints. It is an in-route operation. The next one is delete and insert procedure. It takes a node, deletes it, and inserts it in the best possible place among the route. It allows us to change the number of customers in the routes and decreases the number of routes. It is both in and between route operations. So here you can see node 5 before the delete and insert operation, and after it deleted. So initially 5 is in this red path. After deleting and placing it in this blue path, you can see that this X crossing over here is avoided. So next, coming to the implementation, here we build an API using heuristic design in Java and then implement local search algorithm. Code scoring, we then code scoring function as part of the API. And then we combine the optimization algorithms, that is meta heuristics, with score calculation by rule engine called rules. And then we use Swing UI for user interface here. Next, coming to the VRP scoring function. When writing the scoring function that allows to compare the quality of different solutions discovered by the search algorithm, we finalize the solution score by a number representing the cost of each route traversed by a vehicle. it doesn't really matter whether we optimize for the fastest or shortest route. In both cases, you have to get the number based on the length and type of route connection between the points in the entire route. To search the solution space efficiently, it has to calculate the score quickly. So this means you should evaluate any IO operations during the score calculation, especially accessing files on the system or API services over the network. You have to calculate the complete distance matrix for all locations which are part of the problem and keep that matrix in memory while the application is running and determine the final and optimal solution as a final result. Then there's a project called OpenStreetMap, which contains geographical data about the whole world. Data is contributed and maintained by the community and it is open. This project gives us the travel time between any two given points on a map to extract the exact type of information that we need from OpenStreetMap data. Specifically, we need to find route connection between points of interest and the time it takes to traverse such connections using selected type of vehicle. Then here, we also an important feature called real-time planning in this project, in which we can provide new information about the problem while the server is running. It will take that into account and give the best solution according to that. That is, to say in other words, when there is a dynamic change in inputs, it will still take that into account and give the best possible solution according to that. So while designing VRP, you should definitely keep in mind about the hard and soft constraints. So under hard constraints in this VRP, we have vehicle capacity. Vehicle capacity, a vehicle cannot carry more items than its capacity. And then we have time windows. This is only in the case of capacitated VRP with time windows. Under this, we have travel time, customer service duration, customer ready time, and customer due time. You have to always make sure that hard constraints must not be broken. Then coming to the soft constraints, here we have the total distance, that we have to try to minimize the total distance driven by all of the vehicles in order to reduce the fuel consumption. Soft constraints should not be broken if it can be avoided. Hard constraints are weighted against other hard constraints. Soft constraints are weighted too against other soft constraints. Hard constraints always outweigh soft constraints regardless of their respective weights. So now coming to the result, now let us go to Eclipse and run the project and see how it goes. So basically here you can see these are the input files. And now let's run the program. So once I run the program, you can see the screen here. So these are the input files here. On the left hand side, you can see the input files. So I'm selecting one of the input files, and here you can see this is the depot, and each dot here represents the customer locations, and the number on each dot represents the capacity to be delivered to that particular customer or demand location. So now let's click on solve. Initially, you can see the distance is 1079, and as the algorithm is running, it finds the optimal route. And so now finally, you can see that the distance is reduced to 743. These are the vehicles. Here there are 6 vehicles and 32 customers. And each customer has different capacity to be delivered to that customer. So this is the best route here. And as I mentioned earlier, I have also implemented real-time planning. So now the program is running. Still I can add number of customers if I want to. So you can add any customer by right clicking anywhere on the screen. So let me add customers. You can see that it's still taking that into account and solving and giving us the best route. So let me add one more customer. So you can see it finding the best route. And coming to the worst case scenario, see here, we have 6 vehicles, each vehicle with a capacity of 100. So total the vehicle capacity is 600. So now let's see what happens if we increase the capacity to be which is to be delivered to the customers beyond the vehicle capacity. That is, if it is more than 600, let's see what happens. So let me add more customers. So now you can see that the capacity to be delivered to the customers is greater than the vehicle capacity, and that's why the application is showing the solution as not feasible here. And you can see that the vehicles, since it has exceeded the limit of the vehicles, it's being highlighted in red over here, the vehicle capacity. So let me stop this here. Here you can see that the hard constraint has broken, and that's why the solution here is not feasible. Here you can see the number of the amount of capacity exceeding or the weight of each vehicle. So now let's go back to the presentation. And one more thing, here you can even save the solution by clicking on the Save As button and clicking Save. It saves the solution in XML format. Going back to the presentation, here I have attached the same screenshots here. So this is before running the program. Here, now I have selected the input file over here, and this is before solving. You can see the distance as 1059. And after solving, the distance has reduced to 743. And finally, this is the worst case scenario where it has exceeded the capacity, and you can see that the solution is not feasible here. And finally, coming to the conclusion, here in this vehicle routing project, a rule engine such as rules is great for calculating the score of a solution of planning problem. It makes it easy and scalable to add additional hard or soft constraints. It does incremental score calculation without any extra code. This is a huge performance and scalability gain. Constraint streams and rules score calculation give this huge scalability gain without forcing you to write a complicated incremental score calculation algorithm. Also, the time complexity of recursive based approach algorithms is big O of 2 power n, whereas the time complexity of the meta heuristics approach, which we have used in this project, is big O of n, which is much better than the traditional method. Coming to the future work, machine learning model can be incorporated into this application that can improve the solutions provided by this application. Machine learning models can be built for these factors such as previous solutions, historic weather data, historic traffic data, and the cost to deliver can be calculated based on historic date of time to deliver fuel cost and equipment cost. So this is my project on VRP. Hope you like it. Thank you.